The third strand in the physical science standard is covering energy. So the overall strand states that students will describe and investigate energy systems relating to the conservation and interaction of energy and matter. So we're going to look at several different properties of waves. First is describe a mechanical wave property: speed, wavelength, frequency, amplitude, and how waves travel through a medium. So amplitude would be how high from the resting point, the middle point of the wave, to the top of the crest. How high that is, that would be your amplitude. And your frequency is how often in a certain frame, like you set a certain time period or you set a certain distance, how many wavelengths go through that distance or that time period is your frequency. The mechanical wave properties, some of those are that they're able to move through a medium. So you have to know what a medium is. A medium is anything that has some sort of mass. So how sound waves work is that it's vibrating particles. So a medium can be air, any liquid, it can be the ground, it can be any solid, but most waves need sound waves need some sort of medium to travel through. Light waves do not. Light waves can travel through space. Because there's no particles in space, you will not have sound because there's no medium, but light can travel through space. There's other vibrational waves and different things. They all need a medium to travel through as well. And then wavelength is the distance from one crest to another crest or from one trough to another trough. So energy that are in waves can be transformed into other forms of energy. What are some of the different forms of energy? We have kinetic energy, potential energy, there's sound is energy, heat would be energy. So you can have all these different kinds of energy get transferred from one to another. And that's called the transformation of energy. We see that a lot with kinetic to potential. If something's falling, your potential energy is getting converted into kinetic energy, but this can happen with waves as well. Recognize that light can behave as a wave. So diffraction is when two waves, or diffraction is when a wave is passed through some sort of diffraction grating. It's called. It basically will bend the wave. So something that will bend a wave is like a prism. So light goes through a prism and gets bent, and that's why you see the rainbow of colors on your wall, is because the light is getting bent. The different wavelengths bend at different angles, and so it separates the different wavelengths. So that is one example of how light behaves as a wave. Interference is when two waves come and overlap each other and they change the other, they have a sum of the forces, some of the waves that can cancel out some of the crests and some of the amplitudes. Distinguish between temperature, which is a measure of the average kinetic energy, and heat, the quantity of thermal energy transfers due to a change in temperature. So heat looks at the change in temperature and depends on also the mass of that quantity of substance, whatever you're measuring. And so heat is transferable. So if I put hot water in cold water, eventually it's going to come to an equilibrium in temperature, and that cold water has gained heat, the hot water has lost heat, and since we've mixed them, the heat lost by the hot water is actually equal to the heat that's been gained by that cold water. It's the conservation of heat. Compare and contrast methods of heat transfer and the interaction of heat with matter with conduction, convection, and radiation. So what's the difference between these three? Conduction is the transfer of heat with direct contact. So the particles of one material are transferring their energy to another material. So when you touch a hot pan, that is conduction. The heat is traveling from the pan to your hand. When you touch ice, that's conduction. The heat's going from your hand to the ice. Convection has to do with a heat being transferred with a current. So one example is in a house, in a two-story house, heat rises. So heat will go up a stairwell, and that will push colder air down a stairwell also. So heat rises, and so it's less dense than cold air. So heat will rise, cold air will drop, and there can be a circulation of heat through your house. There's convection currents similar to that in the oceans, where you have warm water and cold water circulating because of their temperature differences, convection. And if any of you have an oven at home, some ovens are called convection ovens, and that's because they have little fans inside of them that will blow the air, and it's supposed to distribute the heat within the oven evenly, and it will move the air around in the oven to give an even heat for baking. And radiation. Radiative heat is when you can feel heat waves coming off of something. So at my house I have radiators, hot radiators that have the hot water that goes through them. We have a boiler and it has hot water going through them. So I can, in the winter, if I put my hand close to those radiators, I can feel heat coming off of those radiators. That's an example of radiation. Radiation is very important because that is how this energy, the heat from the sun, reaches Earth, is through radiation. That heat is traveling through space to Earth, and that is an example, a very important example of radiation. Recognize that the production of electromagnetic waves is a result of changes in the motion of charges or by the changing in magnetic field. So electromagnetic waves have a huge spectrum. They go from radio waves all the way up to gamma rays. Radio waves are very, very long, low energy waves. Gamma rays, very, very short, high energy waves. So and when electromagnetic waves are very related to each other. So electricity forms a little bit of magnetism around a wire. If electricity is flowing through a wire, there's a small amount of magnetic energy, the magnetic field that's around that wire now. Or magnets are able to create a little bit of electricity. So they are very much combined, they're very much related and connected to each other. It's called an electromagnetic wave because they are always together. Compare and contrast segments of the electromagnetic spectrum based on frequency and wavelength. So I just alluded to that, where you have very long wavelengths, very short, long frequencies, and so it's very low energy. Frequency and wavelength, if you have a high frequency, you're going to have a very short wavelength. If you have a very long wavelength, you're going to have a very low frequency. They're inversely related to each other. Now, frequency and energy are directly related to each other. So the higher the frequency, the higher the energy. So radio waves, one wavelength can be as long as a football field. So that is a very long, very, very long wavelength. and so it has a very low energy, and they're in the air, everywhere with the radio waves. Now, on the very far other end of the spectrum are those gamma rays. So gamma rays have a very, very short wavelength, like less than a water molecule. They're very tiny. It's going to have very, very, very high energy. You wouldn't really want gamma rays flying around because they can be very destructive. The sun does produce all forms of electromagnetic radiation, and some does reach the Earth, some gets trapped up in our atmosphere and doesn't reach the surface. So the sun does produce those gamma rays. Humans have learned to harness the energy in gamma rays. If you've ever heard, Lincoln has had what's called the gamma knife, and it's a way that they can do treatments on different brain cancers or inoperable cancers, that they can use gamma rays in order to treat those without going into actual surgery. They use this machine that is called the gamma knife, and it uses gamma rays. Okay, recognize that nuclear reactions, fission, fusion, radioactive decay, convert a fraction of the mass of interacting particles into energy, and this amount of energy is much greater than the energy in a chemical reaction. And this energy is related based on E equals mc squared, Einstein's famous equation, that a little bit of mass gets converted into energy in these kind of reactions. So the nuclear bomb, the atomic bomb, how that works is it's taking uranium and plutonium, and it starts this nuclear reaction where uranium and plutonium, they get split. It starts a small reaction where the uranium splits. That splitting of the atom releases a lot, compared to an atom, releases a lot of energy. Now, one atom releases very little energy compared to the energy around, but when you have a huge amount of uranium that's in an atomic bomb, that first uranium atom will start a chain reaction that will light off all of the other uranium, and it will split all those uranium atoms to give us that huge energy release in the atomic bomb. Interpret the law of conservation of energy to make predictions of the outcome of an event. So, kinetic energy and potential energy, and that is we're going to look at the transfer between the two. Potential energy, when you're far from the ground, you have high potential energy, very low kinetic, and it gets transferred until right before you hit the ground. You have very high kinetic energy, very low potential energy. We'll have some questions on that. Identify endothermic and exothermic reactions. So endothermic reaction is when when heat is getting added to something, and that usually if you feel that reaction, like in a test tube or something, it would feel cold because it's taking energy from outside and taking it to help fuel that reaction. If you think about it in terms of what the molecules are doing, the molecules are actually speeding up, so they're gaining energy from the outside, from outside the system. Exothermic is the opposite, where it's releasing energy, and if it would feel hot, or warm. That test tube, if you had an exothermic reaction occurring, would feel warm. If you think about what the molecules are doing, they're actually slowing down. So they're releasing their energy, they're giving their energy to the outside of the system. Temperature is a measure of kinetic energy, so it's releasing heat, and releasing that energy, the molecules itself will have to slow down.